What if consciousness wasn't something special happening in your brain, but something that could be measured, calculated, even assigned a number? That's the radical claim behind Integrated Information Theory, or IIT. One of the most influential and most controversial theories of consciousness in modern science. The theory was developed by neuroscientist Giulio Tononi, and it starts from an unusual place. Instead of asking what causes consciousness, it asks a stranger question. What does consciousness actually feel like from the inside, and what physical property could possibly produce that? Tononi identified a few core features every conscious experience seems to share. It's unified. You don't experience the color of this scene and the sound separately. You experience them together as one moment. It's specific. This exact experience and not some other one. And it's information rich. Even a simple visual scene rules out a near infinite number of things it could have been instead. From these observations, IIT makes a bold move. It proposes that consciousness is identical to a system's capacity to integrate information, to combine data in a way that can't be broken down into independent parts without losing something essential. Tononi gave this quantity a name, phi. The Greek letter phi represents how much integrated information a system has. The higher the phi, the theory claims, the more conscious that system is. This is what makes IIT different from almost every other theory of mind. It's not just descriptive, it's mathematical. In principle, you could calculate the phi of a brain, a computer chip, or even a thermostat, and get an actual number representing how conscious that system is. And this leads IIT to some genuinely strange conclusions. Because phi depends on how information is integrated, not on what the system is made of, IIT predicts that consciousness isn't unique to brains. Any sufficiently integrated system, biological or artificial, could, in principle, have some degree of experience. But here's the twist that makes IIT so controversial when it comes to artificial intelligence. Most computer architectures, including the ones running today's large language models, are built very differently from brains. Information in a standard computer chip tends to be processed in ways that are highly divisible, broken into separate, isolated operations. According to IIT's math, that kind of architecture would have very low phi, no matter how sophisticated its behavior looks from the outside. In other words, IIT suggests that an AI system could pass every behavioral test for intelligence, hold a conversation, solve problems, seem self-aware, while having almost no integrated information at all. Behaving conscious and being conscious, on this view, are separate things entirely. This is a direct challenge to a very natural intuition that if something acts conscious, we should treat it as conscious. IIT says the architecture underneath matters more than the performance on the surface. Critics push back hard on this. Some argue that phi is nearly impossible to calculate for any complex real system, biological or artificial, which makes the theory hard to test. Others argue that IIT's math leads to bizarre results, like simple grid-like systems having surprisingly high phi despite doing nothing that looks like thinking at all. Still, IIT remains one of the most cited and most seriously debated theories of consciousness in neuroscience today, precisely because it tries to do something almost no other theory attempts. It doesn't just describe consciousness, it tries to measure it, which raises the question this series keeps circling back to. If consciousness really is a matter of integration, not imitation, then the path to conscious machines may look nothing like the path AI is on right now.